make it quick. All right. So for the regular titration plot, we just use these two columns here, you know, the x and the y. And then for our first derivative, we have to calculate our slope. And so that involves delta x. And so this is the delta x calculation. I could have started it here, but it doesn't matter if I started here or here, because delta x is going to be x final minus x initial. Does everybody see that? X final minus x initial. And then delta y is y final minus y initial. All right, then I get the slope. But what is that slope for? The slope is actually not for the second row. It's not for the first row. There should be a row in the middle here. The slope is supposed to be for the... And so the row in the middle is this volume here. If you go back and look at the volume, I started at 0, I end at 0.1. And so the volume for the slope should be in the midway point, which is here, 0.05. And so this already is offset. And so I could have put it in the first row or the second row. It doesn't matter because it belongs in the middle row, but there's no middle row there. And so is that clear? And so that's where the slope is, right here, because the slope, again, is not for x1 and it's not for x2. It's for x average, 0.05. All right, so then I make a plot. This is my volume. I actually don't have any data at 0.05, you know, that's between data points. But this is the slope, so I got to plot this, the volume versus the slope here. And then I can generate my first derivative. Now, there's a problem. The problem is this. How can I do an overlay? Because the problem with my overlay is I need one x point and two y points for an overlay. I can't have one, it's because of the way Excel works, and maybe somebody can correct me, but for an overlay you cannot have an x point here and an x point here and have two different plots, because then it'll start the zigzag thing. And so what I did here is this. Since I need one volume with two y data, one y data is the pH, the other y data is the slope. And so what I had to do here is I had to generate one of those. And so which one did I generate? And so this is what we did here. F8 and F9. The average of F8 and F9. Well, what is F8 and F9? The average. See, okay, so this is what's happening here, if you can imagine this. pH titration's here. First derivative is offset, right? Okay, now if I want to overlay them, I have to offset either the slope or I have to offset the pH. And so what I did was I left the pH there and then offset the slope. And so what that means is I know what the slope is here and I know what the slope is here, but I want to know what the slope is here. And so all I did was I took the average of the two slopes and said that would be the slope in the middle. And what that does is it does this. You know, it offsets the first derivative so that the data points now match. And so now for this volume, which is a volume I actually have, I now know the pH and the slope. Are you guys following me? And so that's why, this is why there's all this kind of weird offsetting going on back and forth, because I don't have data at those specific X values in order to do an overlay. Now, if you're not doing an overlay, then forget all this offsetting stuff. You don't have to do this. If you're not doing an overlay, then all we need is the yellow column there and the green column and this white column here. But you don't need all this other stuff where we're going back and forth offsetting it to generate the overlay plot. And so I just did the overlay plot so that you could see how they match up. But you know, it's because of the how we're doing. This is called numerical differentiation. You know, if we had a mathematical function, we wouldn't have to do all this stuff. You know, but we don't, because there's different mathematical equations that define that curve. The other thing is we could try to fit the data to one mathematical function. You know, here, I'll show you what I mean by that. Because a titration curve, depending on what part of the titration curve you're in, right, is dictated by an equation. And so if I try to fit my data by adding a trend line, I don't want linear. I'm going to do a polynomial. And the higher order the polynomial is, the better the fit. And so this is about the most flexible mathematical fit we can generate for this. But do you see, I'm not going to be able to have one equation. I can have a composite equation. The composite equation, in the buffer region I'd have this. In this region I'd have this, you know, depending on the x value. Right? But if I could fit this to a single equation, then I can use calculus to figure out, you know, what the slope is at any point. But since I'm not, since I'm doing this the manual way to figure out what the slope is, by taking delta y and delta x, then I have to do all this offsetting business. Okay, we'll continue on here. Hard to draw the trend afterwards.
If I extend the original restriction, it's just because it's like all smashes.
Oh, and is there more data beyond 22 milliliters?
They should be recommended.
No, I mean, that doesn't matter. I know if you extend it, but it would be nice to see more data. It's supposed to go to 35. I mean, that's what we calculate.
Well, yours will be different, right?
Actually beyond 35.
Yours will be
I don't know. Is there another equivalence point beyond there? What is the pH?
pH is like 11.
All right. So let's take a look at how I define the other columns here. And so here's the slope, and here's the average volume for that slope. Oops. Let me go back. Here's the slope, here's the average volume for that slope. Okay, the next thing we're going to do is we're going to take the second derivative plot. The second derivative plot, we take the delta x here. Let's take a look at how I calculated this delta x. We take the delta x here and the delta y here, and then just take delta y over delta x here. And then we have to fix the volume because this volume is between 0.150 and 0.250. So what's between 0.150 and 0.250? It would be 0.2, right? And so that's why I have 0.2 here. If you look at this slope here, this slope would be the slope between 0.05 and 0.150, which would be 0.1. And so you don't have to use this equation, but you know what volume we're after because we're just taking the average volume between those and then generate it. And so it's the exact same thing. We're just repeating it for the second derivative. Is that clear? Enough? These last two columns are for the Grand's plot. That's extra credit, so you don't have to do that necessarily. But that's a Grand's plot. Look it up on the internet if you want to know what it is.